All right, so this is more difficult than the ones we've done before. This is the find the moment inertia of a uniform hollow sphere. And so basically I have a sphere here. Again, I'm going with the z-axis as my axis of rotation. The total mass is m, and the radius of this hollow sphere, think ping pong ball if you need a more visual, is r. Looking at this hoop right here, it's equal to, the radius is rh, so that's this right here is rh. And since I have a triangle here, I know that Pythagorean theorem, r squared is equal to rh squared plus z squared. My generic formula for moment of inertia is the integral of dm r squared. And so I need to get these in terms of a common variable here. So let's first deal with dm. Since it's uniform, I know the density is equal to mass over volume, or in the individual piece, dm over dv. So therefore, the differential of the mass is equal to rho times the differential of the volume. So the volume of this little hoop right here, so if we took a look at it, let's see if I can draw it out better over here. So we've got this hoop right here, and there's a tiny little thickness along here, and I don't know if this is drawn better or not, but it's the way I'm drawing it. So we have this tiny little thickness here. So I know that for a hoop, the volume is going to be basically circumference times this height right here times this thickness right there. Well, the circumference, it is a differential because it's infinitesimally thin. So the differential is going to be 2 pi times the radius of the hoop. And I know I switched to a lowercase r. The uppercase and lowercase r in this case actually do mean the same thing. Times this height right here. Well, this height, if we think about it, if we look at that little segment right there, so again, let's go back to my attempt at a drawing here. We have a hoop with some thickness, a center here. That thickness is basically this arc length right here, and if that's r, this angle here is d theta. So this becomes r d theta. So this is r d theta. And the thickness, I'm just going to make something, it's infinitesimally thin, I'm just going to say dt. That's just, it's some tiny little thickness there. Or, yeah. So this becomes times r d theta dt. And so therefore, dm is 2 pi r dt. It's a constant thickness throughout, even though it'll eventually go away. So 2 pi big R dt, and then we have radius of hoop d theta times rho. All right, so my moment of inertia then would be the integral of dm rho 2 pi big R dt r hoop d theta times r squared. Now this r is the distance from the axis here, so this is radius of the hoop, so radius of the hoop squared. Bring the constants out. These are all constants, so this is rho 2 pi big R dt times the integral of RH cubed d theta. We need to get this in terms of a single variable here because the radius of the hoop and theta will change as we go, so they're both variables. So this is rho 2 pi r dt. Now, if again, go back to our what we're working with here, we have some angle theta here. This is my radius of my hoop. This is big R right there. And we do have a relationship between R and theta, between RH and theta, that I know that RH is equal to big R, the radius of the sphere, times the cosine of theta. And so I can now plug that in here. So this becomes R cubed cosine cubed theta d theta. I can bring that out. So I have 2 pi rho big R to the 4th power dt times the integral of cosine cubed theta d theta. We have a single variable now, so we can now do our limits of integration. And so theta is going to be going, well, basically, I've got a sphere here, and if theta is the angle to where the hoop is, it's going from 0 to pi over 2. That'll take care of half of it, and so then I have to multiply by 2 for the entire sphere. And so we now have 4 pi rho r to the 4th dt. Again, that's my constant. And now we have to figure this one out. And so how do you actually find it? Now, there are various ways of doing it, but this is the physicist way. Now, there are definitely some slick math techniques. The physicist way is to look it up. And if you'll notice over here, this is the standard mathematical tables and formulas. You can also look it up, look up tables of integrals, and I think it's standardized. It's going to be number 303 in all of them. So this tells me the formula right there, where a is equal to 1. And so this becomes, looking at the formula here, 1 over 3 times the sine of theta times cosine squared theta plus 2 from 0 to pi over 2. And again, looking back over here, here's the formula. I'm hoping that it is focused in on it. And that is how the physicists do it. You look it up. And so now we're left with 4 pi rho r to the 4th dt. That is just, again, my thickness. And then we plug things in. If I plug in pi over 2 here, I get 1/3 times 1 times 0 plus 2 minus, plug in 0 here, I get 1/3 times 0 times 1 plus 3. That's equal to 0. This is equal to 2/3. So I get 4 pi rho r to the 4th times my thickness times 2/3. Now, this doesn't really look like much at the moment, but we are about to change that because we do have a formula for rho. This density is mass over volume, which is mass over the density of this thin-shelled sphere, which basically is the surface area times the thickness. So this is 4 pi r squared times dt, and so dt is going to cancel out there. So we're left with 4 pi times m over 4 pi r squared times dt times r to the 4th dt times 2/3. And now we do some canceling, which is which is often the best part. So 4 pi cancels out, dt cancels out, r squared cancels out with 2 of those. And what I'm left with is 2/3 mr squared. And that's the formula for the hollow sphere.